Advection is the bulk motion of fluid molecules, or of particles that are suspended within the fluid, due to a non-zero average fluid velocity. Examples of advection include the flow of a fluid in a pipe, the flow of water in a creek, and the flow of wind. Diffusion without advection occurs when fluid molecules move solely due to random motion. As we have seen before, diffusion is responsible for heat conduction in fluids. When diffusion occurs without any advection, the average fluid velocity is equal to zero. This is due to the fact that the velocities of the fluid molecules in random directions tend to cancel each other out when their velocity vectors are averaged. Convection heat transfer takes place due to both diffusion and advection. It should be noted that diffusion always takes place in a fluid, whether there is a net average fluid velocity due to advection or not. Hence convection heat transfer can be defined as the transport of heat in a fluid, due to advection and diffusion. Note that the word fluid is italicized in the previous statement, to emphasize the fact that convection only occurs in fluids, and not in solids, since the molecules of solids are mostly immobile. Depending on the driving force for the fluid advection, heat convection can be divided into three main types: natural convection, forced convection, and mixed convection. Natural convection, which is also sometimes called free convection, refers to a situation in which the heat transfer process itself causes the fluid to undergo bulk movement due to buoyancy. Recall how in gases, density is inversely proportional to the temperature according to the ideal gas law. Recall too that in liquids, density is also inversely proportional to the temperature. When a part of a fluid that is in close proximity to an object that is transferring heat is heated or cooled, its density changes with respect to the rest of the fluid. Due to buoyancy, colder, and hence denser, fluid tends to sink, while hotter, and hence lighter, fluid tends to rise. Consider the shown cylinders that are both placed in long containers with square cross-sections. If the cylinder is colder than the walls of the container, then the shown convection pattern develops, where the fluid that is in close proximity to the cylinder becomes colder and denser than the rest of the fluid, and hence sinks down. On the other hand, if the cylinder is hotter than the walls of the container, then the shown convection pattern develops, where the fluid that is in close proximity to the cylinder becomes hotter and less dense than the rest of the fluid, and hence rises up. The resulting natural convection flow pattern enhances the heat transfer between the cylinder and the container's walls. Consider the following examples of heat transfer processes involving convection. For a hot oil radiator, the temperature of the air that is close to the hot radiator surface increases. The hot air tends to rise, and creates a natural convection flow pattern as shown. The heat transfer from a candle produces a similar convection flow pattern. Notice that if you place your hand directly above the candle, you will feel a lot of heat due to the hot rising gases. Alternatively, if you place your hand at the same distance, but next to the candle, you will feel much less heat, since your hand will be in the path of the colder air that is flowing to replace the rising hot gases. In fact, the heat you feel when your hand is next to the candle is mostly due to heat radiation, which will be discussed subsequently. Hot air or gases rise through conventional chimneys also due to natural convection. When a container that holds a liquid is heated from below, convection currents develop within the liquid that carry the heat from the bottom of the liquid to the top of the liquid. When the lower density hot liquid reaches the top, it exchanges heat with the surrounding air and cools down, which causes its density to increase. The cooled liquid then falls to the bottom of the container again, and the cycle continues. If the temperature at the bottom of the container is hot enough for the liquid to boil, a phase change into a gas occurs in the liquid layer adjacent to the bottom of the container, and the heat is carried away by the evaporated gas bubbles through the liquid and out into the surrounding air. Fires also create natural convection air currents that tend to supply the fire with fresh, oxygen-rich air from the fire's surrounding. On a larger scale, natural convection due to solar heating causes wind patterns that affect our entire climate. In forced convection, heat is transferred to or from a fluid that is in motion. The motion of the fluid, however, is not due to the heat transfer process. Instead, an outside force such as a fan, or a pump, or simply the movement of the object that is transferring heat through a still fluid, causes forced convection flows that can greatly enhance the heat transfer process. In our daily experience, we can relate forced convection to the myriad of fans that whir around us to cool us or keep us warm. Examples of forced convection include electric fan heaters that use a fan to drive an airflow over the hot electrical coils of the heater and out into the surroundings. Automotive radiators have forced convection both inside and outside the radiator coils. Inside the radiator coil, engine coolant is circulated by a pump from the engine block to the radiator. Outside the radiator coils, the movement of the automobile, or a fan, pushes air through the fins of the radiator to cool them down. Cooling fins on the engine block of a motorcycle increase the surface area available for forced heat convection, as the motorcycle is rolling. We all have a forced convection system that operates within our bodies, to help regulate our body temperature and keep it uniform using blood circulation. Mixed convection refers to situations in which both forced and natural convection play important roles in the overall heat transfer process. This is most typically found in boundary layer flows, such as airflow over and parallel to a flat hot plate, especially at lower air speeds. Due to the no-slip boundary condition, the horizontal velocity of the air very close to the surface of the plate is nearly equal to zero. In this boundary layer, both the forced convection due to the horizontal air velocity, and natural convection that forms vertical recirculation flow patterns, play important roles in the overall heat transfer from the plate. The heat transfer rate, capital Q dot, in watts, due to heat convection from any given object, such as this tank, can be written as the thermal convection coefficient HC with units of watts per meter squared Kelvin, times the surface area of the object that is exposed to convection, in meters squared, times the difference between the surface temperature of the object and the ambient temperature. Note that in heat convection, we use the total object surface area that is experiencing convection, not the cross-sectional area perpendicularly to the direction of heat flow, as in one-dimensional heat conduction. Obtaining an accurate value for the heat transfer coefficient is often difficult, due to the complex nature of most convective flows, that involves combined fluid dynamics and heat transfer effects. One way of obtaining the value of the heat transfer coefficient is by solving the partial differential equations that describe the flow of mass, momentum, and energy. These equations include the continuity equation, the momentum equation in three directions, and the energy equation. Additionally, equations that describe turbulence and other fluid and thermal effects might also need to be solved. Given the complexity of these equations, whose explanation and derivation are beyond the scope of this treatment, it is very difficult to solve them analytically, except for the simplest geometries and flows. The method that is much more frequently used to get the heat transfer coefficient is using experiments. The heat transfer coefficient of a given geometry can be calculated from measurements at various flow rates and temperature differences. A correlation can then be derived that relates the heat transfer coefficient to these variables. The main downside of this method is the time and effort that is needed to set up and conduct the experiments. Another method for obtaining the heat transfer coefficient that is quickly gaining favor is using computational fluid dynamics, or C&D analysis, to numerically solve the partial differential equations that govern the mass, momentum, and energy flow. The main factors that influence the value of the heat convection coefficient are the nature of the convection process, be it natural or forced convection, the geometry of the surface that is undergoing convection heat transfer, the type of fluid. In general, fluids with higher thermal conductivities, higher densities, and higher specific heats tend to provide higher heat transfer coefficients. For example, using a flow of water to cool down a hot object is much more effective than using the flow of air. Furthermore, the higher the fluid velocity, the higher the heat transfer coefficient. The thermal convection resistance is defined in the same way as the thermal conduction resistance, where the heat transfer rate is equal to the temperature difference divided by the thermal convection resistance. The temperature difference in this case is the difference between the surface and the ambient temperatures. Using the equation for heat transfer rate by convection that we introduced earlier, we can set the two expressions for Q dot equal to each other, and deduce that the thermal convection resistance is equal to 1 over the heat transfer coefficient times the surface area of the object that is subjected to convection. The thermal convection resistance has the same units as the thermal conduction resistance, or Kelvin per watt. In order to dissipate the heat that is generated by a computer processor, the heat sink and cooling fan are used. The skin of the processor is made of stainless steel, and its thickness is 0.5 millimeter. It is assumed that heat mainly flows through the top part of the processor, which is square in shape, with a side length of 3 centimeters. The heat sink compound, with a thermal conductivity of 4.5 watts per meter Kelvin, is placed between the processor and its heat sink, to minimize contact resistance. The thickness of the compound is 0.25 millimeters. An aluminum alloy is used to make the heat sinks thin due to its high thermal conductivity and since it can be easily cast into intricate shapes with thin walls. The total surface area of the fin is equal to 0.09 meters squared. The core of the heat sink is made of copper, which has an even higher thermal conductivity than aluminum in order to more uniformly distribute the heat within the heat sink. The heat sink is placed on top of the processor to help keep it cool. When the heat sink's fan is operating, the heat transfer coefficient is equal to 20 watts per meter squared Kelvin, and when the fan is off, the heat transfer coefficient is equal to 1.6 watts per meter squared Kelvin. The ambient temperature is 30 degrees Celsius, and the maximum allowable processor internal temperature is 80 degrees Celsius. Calculate the maximum allowable continuous processor heat generation rate in watts when the fan is off and when the fan is on. We start by calculating the cross-sectional area of the processor through which heat is flowing from the processor's width. We then calculate the thermal resistance of the stainless steel processor casing to be equal to 0.03679 Kelvin per watt. The thermal resistance of the heat sink compound layer is equal to 0.06173 Kelvin per watt. The temperature difference that is driving the heat transfer process is the difference between the maximum internal processor temperature and the ambient temperature, which is equal to 50 Kelvin. For the natural convection case, where the fan is not on, the convection heat transfer resistance is equal to 1 over the heat transfer coefficient for the natural convection case, times the surface area of the heat sink. This gives a value of 6.94 Kelvin per watt. The total heat transfer resistance for the natural convection case is calculated by adding the heat conduction resistances of the stainless steel processor casing and the heat sink compound to the heat convection resistance due to the natural convection acting on the heat sink. This gives an overall heat transfer resistance of 7.043 Kelvin per watt. Finally, the maximum heat transfer rate from the processor under natural convection conditions is calculated by dividing the temperature difference by the total heat transfer resistance for the natural convection case. The maximum heat transfer rate is found to be equal to 7.099 watts. The forced convection case is calculated similarly, using the heat transfer coefficient of the forced convection case. The maximum heat transfer rate for the forced convection case is found to be equal to 76.44 watts. We notice that as expected, the maximum heat transfer rate for the forced convection case is much larger than the one for the natural convection case.